Hi guys, I'm Prof Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in Kempten, the very south of Bavaria in Germany. This is part of my lecture on measurement technology, talking about chapter 6, resistances. For today, I want to talk about the final part, part 3 of the chapter resistances, which is just a little about why measuring resistances is so useful. The reason for that is quite simple. Resistance can be connected to a large number of physical quantities out there. Starting with some simple examples. First one, potentiometers. Potentiometers are available in a variety of forms, twisted, moved along, so that you can do measurements of the distance or the angle. So, potentiometers correlate resistances to angles and distances. That's awesome, because it can be used for a variety of distances, from millimeters to centimeters up to meters. They are somewhat restricted for very large distances and very small distances, but overall it's a very simple way of measuring distances using a resistance, which can be then converted into an electrical signal, and that can be easily used in any system you can think of. Simple example, very impressive in its usage. Think of robot arms. Think of any movement done out there in industries. Those potentiometers are most of the time enough or able to give you the corresponding angles and distances which are necessary for that industrial process. Another example, temperature. It's very well known that, for example, platinum has a very linear relationship to the temperature concerning its resistance. Meaning, for example, you could write down formula looking like that, plus alpha times T minus T0. So there's a constant in there, and to be honest, there might be other terms with other constants in there and with quadratic behaviors and so on. We don't really need to care about too much, because drawing the dependency of that resistance in respect to the temperature for platinum, that's quite linear. That also holds for many other materials out there. Think of copper, for example. It's also quite linear, not as linear as platinum, but that's the interesting point. Even copper had a comparable constant over here like platinum has, meaning it changes its resistance in the same range as platinum does. So, heating up a wire means changing its resistance like heating up a real platinum resistance. That's interesting somehow. Talking about that, often you read something like PT100 or something like that. That 100 corresponds to our base resistance, which would be 100 ohms in this case. And out there are also like PT1000s, but there are also other temperature sensors like a nickel or chrome sensors, which just have another type of material, therefore have other constants and need another treatment. For our purpose, looking at that means we have something like a temperature dependence, which looks like R0 plus alpha times R0 times the change in the temperature. And now you see, to correlate that stuff to the circuit bridges, we get a small variation over here. Talking about platinum, changing the temperature about 10 degrees will change the resistance by about 1 ohm for a PT100, which is quite measurable. It's not too hard to measure that resistance change, and which is enough to make those resistance temperature sensors very widespread and very used out there in industries and any which way. It's obviously why, because it's such a simple technique. It's just measuring the resistance. Very nice example, very good example. Corresponding to that measuring of the temperature, you could use the temperature measurement to measure other quantities, like the level, the fill level of a tank. Just putting in a resistor which is changing its resistance due to the temperature. And now when the fluid touches that sensor, that heat will be able to dissipate better away from that sensor. And so just measuring the temperature can allow you to measure the filling level of a tank, for example. Or there are other examples how temperature can be, again, used indirectly to measure other physical quantities. Moreover, there are sensors for, as I said, measuring gas concentrations. For example, the concentration of oxygen. So that's a special material which reacts with the oxygen in its environment. Very good example. Moreover, there are examples of measuring the light intensities, meaning we have some photoresistors which have a very strong dependency on the reaction to light, changing their resistance, meaning we have somewhat ohm range over here, kilo ohm range over here, and mega ohm range over here, at the very steep places, correlating to a lightning change of 10 to the minus 2 to a light change 10 to the 4. So that goes along 6 orders of magnitudes as the resistance itself also does. That gives us some other problems indeed. Think of that mega ohm. Now measuring the voltage along a mega ohm resistance can be quite complicated because our measurement devices most of the time also have only resistances in the mega ohm range. So we get into that area where those systematic errors for measuring voltages and currents with real voltage or current meters get important. There are many more other examples for correlations of the resistance to a physical quantity. As I said in the first part, that's something a physicist would expect anyways due to thermodynamics. Thermodynamics couples all physical quantities to each other. Some are coupled strongly, some are coupled weakly, but most of the time, or even to be honest, all the time, all physical quantities are coupled somehow. And that means the electrical resistance is coupled to any other physical quantity of that object somehow. Sometimes very weakly. Think of copper or platinum and its coupling to the oxygen concentration. That's very weak. There's some very, very tiny coupling we could never get to measure, but there would be a very tiny small coupling. On the other hand, it's very obvious when stretching or compressing a resistance, we will change the value of its resistance at all. That's used, for example, in another type of measuring equipment, which is called strain gauges. Strain gauges simply use the fact that we have a resistor which is stretched or compressed, and by that changes its resistance, and that can be measured. That's very usable for small distances, and on the other hand, for very fast distance changes, for vibrations, for example. Anyways, to come back to what I've said beforehand, for me it's somewhat obvious that resistances of materials will change due to any other physical quantities. The idea behind that is quite simple. We have a material and it reacts, it has physical quantities and reacts to the physical quantities surrounding it. That's obvious somehow. And now the resistance is one quantity in that material we can measure quite easily. It's electrical. There are easy ways to get a value for that resistance. And by that, we get to know of all the other quantities indirectly because they would or will change also. To get a certain change for a certain physical quantity, we learned everything we need to know because we learned about the circuit bridges, which allow us to focus on some specific physical quantities. But overall, measuring resistances, we are able to measure a whole range of physical quantities out there. If you like that stuff, just subscribe and see you next time. Have fun.